Hello, I'm Kenneth Cukier, Senior Editor. You're listening to Babbage, a weekly conversation on science and technology. On this show, we'll ask, what does new research teach us about why matter exists? Neutrinos, one of the smallest particles in the universe, might hold the answer.
During the Big Bang, matter and antimatter were created in equal amounts. But we know that's not where we are now. The universe is made of matter and all of the antimatter is gone. So there is a fundamental difference between antimatter and matter, and we don't really understand what that difference is.
That was Professor Mark Thompson of Cambridge University, who works on the neutrino experiment DUNE. More about that later in the show. First, nobody knows exactly how the brain works, but scientists keep trying to find out by scanning the brains of test subjects while they perform certain tasks. Thousands of scientific papers have come out of such experiments, but now a new study puts the validity of the scanning technique into serious doubt itself. With me to uncover the story is our science correspondent, Tim Cross. Hello, Tim.
Hi, Ken.
Tim, let's start with the basics. What are the scientists trying to achieve by scanning brains?
So this is a technique called functional magnetic resonance imaging, fMRI, which people might be familiar with. And the idea is you use MRI scanners of the same kind you get in hospitals to diagnose disease to look inside people's brains as they carry out various kinds of tasks. And the trick is that MRI scanners are sensitive enough to pick up signs of blood flow in the brain. And so the working hypothesis is, thinking is hard work. To do thinking, your neurons need blood, they need glucose. And if you can track how blood is flowing around the brain, you can see which neurons are working harder than other sorts. And it might give you some idea of which parts of the brain are involved in different kinds of thinking.
And this has been foundational for brain research.
Yeah, it's been absolutely revolutionary, which is a word that's sort of chucked around too often, but I think probably does apply here. It's about 20 years old, and all kinds of papers have come out of it. And you've probably seen there are pictures of people's brains with little blobs of colour on them. Those are all fMRI scans. They put people in these scanners. They get them to do things like mundane things like recalling directions to explore how your sense of space works or reading other people's emotions. And then there's been the more sort of spectacular headline grabbing stuff about using these things as lie detectors or to even work out what people have been dreaming about. And we should say, it's been revolutionary. It's foundational. A lot of people have been quite critical of it, not because the technology doesn't work, but because people have maybe been a bit too keen to make sort of big extrapolations from it.
And now the problems have strengthened the hand of the critics. So let's look at the problems. What has gone wrong?
The critics have identified a couple of problems in the past. So one is the sample sizes tend to be quite small. The other is that, the changes you're looking for here are tiny, really, really small. And there was a famous deliberately provocative paper that came out in 2009 where they put a dead Atlantic salmon in an MRI scanner and said, hey, we can find traces of brain activity in this dead fish. So, like I said, there's been this sort of bit of skepticism around it. But this new paper is much more fundamental than that. And basically, the way fMRI works, it chucks out so much data that you need computers to interpret it for you. You need, computers to analyze the images. And this team of researchers, led by a guy called Anders Eklund from Sweden, they found that the algorithms underlying those computer programs essentially are based on erroneous statistical assumptions. And the upshot is that they throw out false positives. In other words, they say something's happening when actually it's not.
So how many papers in the field are now in doubt?
Dr. Eklund, when I spoke to him, said, the figure he was using was around 40,000 papers out there, something of that order, that make use of this technique. He and his co-authors have sort of run the numbers, and they reckon somewhere in the region of 3,000 of these might be, flawed enough to be fundamentally wrong. The problem is, unless we go back through all 40,000 of these papers and correct for these errors that, unbeknown to anyone, have been there for decades, we're not going to know which 3,000 it is. So the entire field now has this sort of massive cloud hanging over it.
And no one was able to identify that this problem, these statistical flaws in the algorithms that were used to analyze the data, existed.
It's not necessarily that the statistical assumptions were foolish or wrong. It's just that this is the first time anyone's been able to and bothered to really rigorously test them.
And so what does this mean for other domains?
Well, this is the big question. I mean, it's not, neuroscience is hardly unique in, needing computers to make sense of all the data that's thrown off. I mean, everything, astronomy, genomics, physics, computers and data interpreted by computers is just a feature of modern science now. So it does make you wonder, is there just one skeleton in this particular closet? Or, if we start looking, might we find similar problems elsewhere?
That's right. We stand on the shoulders of giants and we bury our skeletons in the closet. That's science. Thanks, Tim.
Thanks, Ken.
If you have something to add about this week's show, please find us on Facebook or Twitter. You can tweet us directly at Economist Radio or email us at radio@economist.com. Next, we move on to particle physics. Theories suggest that at the time of the Big Bang, matter and antimatter would have come into existence in equal quantities, only to annihilate one another and leave behind nothing but radiation. But of course, there's more to our universe than a vast empty space. Some matter escaped this process of annihilation, which enabled galaxies, stars, planets, and ultimately human beings to come into existence. How some matter escaped is still unknown, but physicists believe that neutrinos could be part of the answer. Our producer, Louisa Field, recently visited the largest conference dedicated to this tiny, remarkable particle, Neutrino 2016 in London. She joins me now. Louisa, hundreds of neutrino enthusiasts were at the conference. Why are physicists so excited about this particle?
So the neutrino is a very curious particle. It's at least 5 million times smaller than an electron. And it's also very antisocial. It can pass through something like 10 trillion kilometers of lead without interacting with any other particle on its way. So actually also billions of them are passing through you and me right now, undetected, and we can't feel them. They're just there.
Right. And so what makes them so special?
The reason physicists are so excited about neutrino is that they have this really remarkable ability to flip between different neutrino types. This is what physicists like to call neutrino flavors. So we have the electron neutrino, we have the muon neutrino, and we have the tau neutrino. And the neutrino can sort of flip between these different types. So it would be like strawberry, chocolate, and vanilla can flip into being strawberry, for example. This oscillation between different neutrino flavors is both true for the neutrino, but also for its counterpart, its sort of evil twin, the antineutrino.
So it's like Jekyll and Hyde, or the ego and the alter ego. Got it. So what were the scientists at the conference hoping to find?
Ultimately, they want to find out why there's more matter in the universe than antimatter. And maybe if they can find out how neutrinos act differently from antineutrinos, then they can begin to sort of chip away at what the answer might be. Specifically, how they morph between those different types of neutrinos. So this asymmetry that the physicists are looking for, they call it charge parity violation or CP violation. So that's the term we're going to be hearing a lot. And it really means that there's a violation of symmetry between matter and antimatter. So nature normally favors symmetry, but they're looking for something that's breaking this symmetry so that the neutrinos and the antineutrinos are acting differently. And that would be this CP violation.
Okay, so let's turn to a clip with you and Morgan Wasco of Imperial College London. He's part of the Tokai to Tamioka experiment known as T2K, for a deeper explanation.
Charge parity symmetry is the stipulation that the laws of nature would be the same if you looked at everything upside down in a mirror and changed all matter to antimatter. It's one of the fundamental space-time symmetries that we explore in particle physics, and we have seen this kind of symmetry violation in experiments with quarks. The level of that symmetry breaking is too small to explain how all the antimatter disappears and it's left with just matter. So we need something with a bigger symmetry breaking, and the hope is that we might see a big symmetry violation in neutrinos. And so that's what we're working on right now, is experiments with both neutrinos and antineutrinos using flavor oscillation as the tool to study that symmetry.
So how is your experiment set up?
We have an accelerator neutrino beam. So we take high-energy protons from the main ring accelerator at the J-Park facility. That's the Japan Proton Accelerator Research Complex in the town of Tokai in Japan. And we create our neutrino beam by impinging that high-energy proton beam onto a carbon target, and there's a spray of high-energy particles that comes off of that. We focus the beam, and we also filter the beam. So we can run in a mode where we keep positive particles, or we can run in a mode where we keep negative particles. And with the positive particles, we end up with a beam that's predominantly neutrinos. And if we focus the negative particles, we end up with a beam that's predominantly antineutrinos.
So at the T2K experiment, they've tested with a neutrino beam and an antineutrino beam.
Yeah, that's exactly right. So the particles, they travel through 295 kilometers of Earth. They then hit the detector, and the scientists, they then measure how many of the neutrinos have flipped from muon neutrino to electron neutrino. And then they do exactly the same for the antineutrino beam. And then they go in and they compare the numbers so they can see if some sort of symmetry has been broken or not. I think we should hear from Dr. Vasco again about the exact results.
We're the first experiment to have measured an asymmetry in the electron neutrino appearance and the electron antineutrino appearance within the same experiment. What we found was an appearance of 32 electron neutrinos and just 4 neutrinos. We saw a little bit more electron neutrino appearance. We expected 27 and we see 32, and a little bit lower antineutrino appearance. We expected 6 and saw 4. So what we're seeing is an asymmetry in the appearance rates of neutrinos and antineutrinos. And in fact, our data are a little bit more extreme in the difference between neutrinos and antineutrinos than would be predicted by the model for charge parity symmetry violation. But so this gives us a 90% confidence result right now, which is not very statistically compelling, but it's enough to start to be interesting, and we're quite excited about it.
So in other words, Dr. Wasco is saying that although they have a 90% confidence in the finding, that's still not good enough to call it a scientific discovery.
Yeah, exactly. It's not a scientific discovery, but it's definitely enough to be very intriguing, and particularly because they are the first experiment to have results on this specific question.
Now, T2K was not built specifically for this type of experiment, but other experiments are underway.
That's right. I think we should hear from Professor Mark Thompson of Cambridge University, because he works on the next generation of neutrino research. It's the experiment DUNE, so a completely different experiment, much bigger experiment than T2K, which we've been talking about so far.
DUNE really is the next step in our kind of decades-long program to really understand the neutrino as precisely as possible. So we're doing many, many new things. Firstly, we're building a neutrino beam that is more powerful than has been built before. So that's important, because if you're doing neutrino physics, you need lots of neutrinos. So we're going to make lots of neutrinos with a very powerful beam. We're firing that beam 800 miles, so that's further than the current neutrino beams, and that makes you more sensitive to certain physical effects. So that's important. And then we're building very, very large sensitive detectors underground. So we're building the idea is to build 4 detectors, each of which is 17,000 tons of liquid argon. And we're putting that a mile underground. And the beauty about this technology is every time a neutrino interacts in that liquid argon, you get a beautiful photograph of all of the particles that come out of that interaction. And that enables us to measure the properties of what's happened in what the neutrino has done much more precisely than in previous detector technologies.
17,000 tons of liquid argon? What's that?
It's just argon that has been cooled down to a really low temperature. And the reason why they use it is because argon lets the physicists see the neutrino interactions really clearly. So the more argon you have, the bigger the detector you have, the bigger the chance is that you're going to see interactions. And that's what the physicists are looking for. They're looking for these specific patterns. So the size of DUNE is equivalent to an Olympic swimming pool dug 6 times deeper. And then we put this a mile underground. So it's a lot of work, and it's a massive experiment. So it's going to take them a while before they actually get the results.
So when do we expect to get those results?
So they're going to start collecting data around 2026. And then, of course, they have to analyze it and all that sort of thing. So we're going to have to sit put a bit before we get the results. But once we have them, we can really say a whole new saga begins, because we want to be then figuring out why the neutrinos and the antineutrinos act differently. So there's a big why question here that this experiment doesn't explain. It just sort of gives us a spark to go on and get on in this research. And in the end, what we want is to explain why matter is here.
And are there any other ways of finding this out?
Yeah, so there's loads of other experiments who are looking differently at this question. Some experiments are looking to see if neutrinos could flip directly between antimatter and matter, so directly from neutrino to antineutrino. So that's a different way of trying to answer this question. But again, they're also far into the future. And I think our best bet to actually answering this and getting closer to the answers is with big experiments like June and looking at oscillation differences.
That's great. Thank you very much, Louisa.
You're welcome, Ken.
That's all for this episode. You've been listening to Babbage. For more stories on science and technology, pick up the forthcoming issue of The Economist. I'm Kenneth Cukier. In London, this is The Economist.